We'll take a look at stability and oscillation of a P-only controller and do this for the temperature control lab. So to get started, here's the link, and it has all of the source code and other things that we're going to be going through today, generating a second order model, the simulator, and other things. Alright, let's go ahead and get started. We want to determine the closed loop behavior of this P-only controller with the TCLab, including oscillatory behavior and stability. We want to be able to use some of the background information on stability analysis. If you select that link, it'll take you to things like route array, root locus, and Bodie plot. So for the temperature control lab, we want to determine a second order model between the heater and the temperature. So that's our output, and then our input is the heater, and we want to model this as a second order system. And then we'll put that into a control loop with KC, and then I'll call this our GP. That's our process transfer function, and this will be our temperature right there, and we have this as our Q1 value. We'll feed this back, and we'll compare the two and have a temperature set point. So with this simple diagram, we're going to make a closed loop prediction. Our closed loop is going to be equal to the direct divided by 1 plus the loop, or you can do the block diagram algebra. So the direct, all of the transfer functions that are in the line between the thing at the start and the thing at the end. Alright, so that's going to be Kc times Gp of S, and divided by 1 plus whatever's in the loop right here. So Kc Gp of S. So that's a shortcut way for simple feedback systems. And so we're going to take this model over here, the GP, and plug it in here and determine what values of Kc for which this is stable, or when does it oscillate. We can also use a simulator. I'll show you that to you in just a second. But let's go ahead and get started just generating the parameters of our model. We have Kp, zeta, and tau s, and that's going to make up our second order model. So to do that with the temperature control lab, we're going to import some packages like NumPy, Matplotlib, Pandas, and Gecko, and the TCLab and time. We'll import data. We need to generate our data first, or we can just, if we don't have a TCLab connected, it'll pull something from the web. Okay, so data.csv, it looks for that first and tries to import it. If it can't find it, it tries to generate it. Here are some of my steps, and I'm just going to leave Q2 off. I'm going to connect to the Arduino lab and write a header file for my data file, and then I'll run for 10 minutes. Okay, so that's going to be 601 time steps. I'll set the heater value, that's the Q1D up above, and then Q2D is going to be 0. I'll print out each time what happens with Q1, Q2, T1, T2. I'll wait for 1 second. I'll open up a file and write a line in that file, close that file, and then I'll close the connection to the Arduino. And if I don't have an Arduino connected and I don't have data.csv, it's going to go out and just grab that file from the URL. Alright, I'm going to read the file name, and then let's go ahead and model a second order system of the TCLab. I'm going to do that with Gecko, and I'm going to insert the time values, and then I'm going to make a new parameter that I want to estimate. I'm going to give it an initial guess of 1, a lower bound of 0.5, an upper bound of 2. Then tau s, same kind of thing, this fixed value parameter, 1 value over all the time points. Give it an initial guess value of 50 with a lower bound of 10, upper bound of 200. And zeta 1.2 with the lower and upper bounds. I'm going to have my initial value from T1, and I'll just take the very first value. Q1 is going to be a parameter. I'll just set that equal to 0. I'll load in some values later. Alright, and then I have x, and then I have TC1. So what I'm doing here is I'm just breaking up this second order equation into two equations. And I'll go ahead and write it out. X equals TC1, the derivative of the temperature. And then I have my second order equation right here. Okay, it's kind of long. Let me make this just a little bit wider so it doesn't drag onto both sides or wrap around. Alright, so let me just show you this briefly so you know where this equation is coming from. This is just our second order equation that we want, and what we're going to do is just start with the second order equation, which is tau s squared dy squared dt squared. Now in this case, this is our temperature. Okay, second derivative of temperature, and then I'll do plus 2 zeta tau s and the temperature, okay, and then plus 1 equals kp times q1. Alright, so what I've done is, because I can't do a second derivative here, I've just defined another state, which is x, and set that equal to dt dt. And then the first derivative of x equals the second derivative of t. And then I can just plug this in. Alright, plug this in right up here, and that's where I get this derivative of x right here. Alright, and this can remain the derivative of t. I put in the deviation value here. We always want to do it in deviation variable form. The derivatives don't matter for deviations because the derivative, if you add or subtract a constant, is going to be the same. Alright, so let's go on through this. We have EV type. I set that to 2. That's a squared objective. And then I turn on the status for all of those parameters to equal to 1, and the feedback status, that means use the measurement for TC1. And then I load in the Q1 values and the TC1 values. Okay, then I'll solve it and print out the parameter values, Kp, tau s, and zeta. I'll say that those are going to be strings, and I just want to take the very first value that's reported. I'll do value 0. Alright, and then I create a plot. This is pretty standard stuff, so I'm going to go through it pretty quick here. Alright, so there's my second order, and let me go ahead and just go ahead and generate that data, and then we'll pause it and then come up with some other values here than are posted in the solution. So it's going to connect. It starts at about 19 degrees Celsius, and there you can see the Q value, Q1 is going to turn on after a little bit. There you can see it's turned on to 80, and then it'll just collect that data, and then we'll be able to analyze it in about 10 minutes. Let me minimize this as it's going through. We'll continue on and just work through some other parts of this. Alright, so we can use our P-only simulator once we have the values. Let's skip on down to determining stability though. We'll come back to the P-only simulator once we have our parameters. So once we do have our parameters, we'll be able to come up with the control stability using the Routh array and the root locus plots. Alright, so Routh array, you need the denominator of the closed loop transfer function. So we had direct. This is our direct divided by 1 plus the loop. And if we just plug in the GP, alright, there's our GP and GP. Then if we multiply the numerator and denominator by this, it just simplifies to something that's in the denominator, and there we want to find the roots of this with the root locus plot, or if you're doing the Routh array, you want to take these coefficients and then we'll just plug them in. This is going to become an. This one right here is going to become an minus 1. And then we have, oh, don't forget both of those. Okay, here's an minus 2. Alright, and then an minus 3. Oh, I have a mistake there. That should be 0. Alright, and then we have b1, which is going to be an minus 1 times an minus 2 minus these two. It's kind of like the opposite of determinant, and then divided by an minus 1. Alright, so that's going to give us this value right here, 1 plus kc times kp. And then b2, that's going to be 0. I had it correct here, but just not correct there. I'll fix that. Alright, and then on down, we do have zeros beyond that. Alright, so this leading edge right here on the left, that cannot change signs. And so in this case, the very first one is greater than 0. So the second one has to be greater than 0 as well. And the third one has to be greater than 0. Now this is the first one that we have where our kc is in the expression. And so in order for that to be greater than 0, we know that kc has got to be greater than negative 1 over kp. Now why would we even do that? Now a controller, if we have a reverse acting controller, if we have a set point change and we want to drive it up to the set point with our PV, then a reverse acting controller is going to increase the output. Okay, but this controller right here is telling us to go the opposite way. It's saying I have the sign wrong. I've accidentally specified a direct acting controller, and when there's that set point change, it's going to go down instead of up. Okay, and as a result, it's going to drive this away from the set point, but we don't become unstable until we get above this limit. Okay, that's what it's telling us. We don't have a problem with stability as long as we are above that limit, even if we specified the wrong direct acting controller. Alright, so in this case we'll plug in, find some new values for kc, but it should be pretty close to this, negative 1.18. Alright, let's do this another way as well, root locus plot. We'll plug in some values on this and be able to calculate our real and imaginary roots. And so here's our imaginary axis and there's our real axis, and then we can drag this back and forth and see how those change. Alright, so when we get to the next part, we'll plug in our second order system and then be able to determine when we are on the left hand side of the plane. You can see one of them is going right over right there into the right hand side, so this is unstable on this side. And then if you have any imaginary parts, that means you're going to have oscillation. Okay, and those roots, those poles will be symmetric across the x-axis. And so if you have one pole up here, you'll always have one down there as well. Alright, this is our root locus plot, and there's some source code for that as well. Alright, and then we'll also calculate when these become imaginary. In this case it was kc is greater than 1.78, but we'll have different values once this finishes running and estimating the values. Okay, so here's some source code for the root locus plot. And then finally we'll get down to this last question. This is kind of extra. It wasn't asked in the question, but just in case you were wondering, we can also predict the offset. So if there's a set point change of plus m, and in the simulator it goes from 23 up to 60, so it's just the difference of those two. And so that's going to be m divided by s in the Laplace domain. And we want to be able to calculate what is TC1 infinity. What is it going to stabilize, go to eventually with enough time. So one of the ways that we can calculate that is multiply by s and set the limit as s goes to 0. And so if we just plug in, okay, right here, we're going to plug in our closed loop transfer function times this step. And that's going to give us, we simplify it out, with s goes to 0, it's going to come up with, this is our predicted change in value for TC1. And so the offset is going to be what we asked it to go to in terms of temperature set point minus what it eventually goes to. And for a P-only controller that's non-integrating, there's going to be some offset. So the temperature set point is requested, but this might oscillate, and there's going to be some persistent offset in the end. Alright, let's see how we're doing with the data collection. And it looks like we've got about 150 seconds left. So I'll just go ahead and pause it right now, and then we'll pick up when it's done. Okay, it's coming down to the last few seconds of the data collection. We went for 600 cycles. I put in range 601 there. And so it should complete now, and then it will estimate, okay, the new parameters. And there you can see the fit from our parameters. You can see a little bit of a deviation right here, but overall it does a fairly good job of approximating that second order response of this system. This is again a linear model of the nonlinear system. But let's go and just take a look at the parameters it gave us. Here we have the gain, the tau s, and the zeta values. I'm going to copy these in, and then we will use those in our, okay, so I'll close this one out. We have our root locus plot. Alright, Kp, tau s, and zeta. And if I just copy these in from the estimated parameters. Alright, I'm going to paste these in. Actually, I need to add some more things here. I need to do the open loop, Kp, and then I have tau s squared, 2 zeta tau, and 1, and then denominator of the closed loop. Alright, and that's going to be direct divided by 1 plus the loop. And we're going to take the denominator of that. I just need to put that into this list. Alright, and then we're ready to plug in the new values. Oh, let me go back to here and grab those. Alright, so here is our predicted values. Alright, I don't need this many significant figures, but since they're there, I'll copy them in. And then we'll run it, and that will give us an interactive plot that we can use for the root locus analysis. Alright, run this with IDLE or the command line. I'm not sure if it's going to run in the Jupyter notebook. What I'll do now is just adjust these, and you can see the black dots. Those are, okay, I just crossed over into the stable region, so it looks like negative 1.29. That is the inverse of our, it's negative 1 over Kp. So right about here is where we cross over into the stable region. You can watch the right up here on the right, those are the real values or the imaginary values of the roots. And as I continue to drag this over, you can see at a certain point it's going to become, it's going to start oscillating. So you see the imaginary numbers that appear there in the roots, and that's at about 2.73. Okay, so those two numbers we need, 2.73, and then right here where it crosses over into the right hand side of the plane, and that's negative 1.27. Okay, 2.73, negative 1.27. And you can see it goes up, but it doesn't, even if you extend this range to higher gains here, instead of 5, you go up to much higher, it's still going to stay on the left-hand side of the plane. So it's going to oscillate, but it will be stable. Alright, I'm going to close this, and let's go over now to our PI, or in this case it's going to be a P-only simulator. And we're going to plug in our second order process right here. Okay, let's see. I want to, let me just go grab that again. Just show you how to grab this. Come down to the bottom, select the get code link. It'll give it to you in raw format. And then you can just paste this into your notebook. And then just replace these 3 values right here with the same thing that you did with the root locus plot. Alright, I'll grab those from the root locus plot and just plug them into my Jupyter notebook and then run this. And then this should give me a P-only simulator. So as I adjust the gain, I've got 2 responses here. I've got one without any output limits, which is going to be the blue, and one with the output limits, meaning that the controller is really constrained to be between 0 and 100. So we're going to get some different values. Let's just see if we can take this unstable by making the gain larger. You can see the oscillation there. It had a little bit of an overshoot versus a steady state value. You can see the KC going up. It just has to recalculate every time it moves that slider bar. So you see it'll update. And then we have the output limit with the offset, and then we have the predicted with the no output limit offset. So I just used that value that we had come up with. That was our M times 1 minus KP times KC divided by 1 plus KP KC. Okay, so that came from down here at the bottom. This formula right there, there's our predicted offset between the set point and the PV value. All right, and we had excellent agreement between the predicted and the calculated, both of them align. All right, and then if I go the other way, at I think it was like 2.7. Okay, this is where we stop oscillating. You can see that overshoot's going to get less and less, and then right about this point, okay, I'm going back up again. Okay, right about this point, there is just a slight amount of oscillation, but it's hardly distinguishable. All right, then I'm going to go down. Now I'm going to go the opposite way. All right, and the controller gain is going down. I'm going to cross into the negative. Now you can see here that that with the constraints, you can't go unstable because you can't cool the TCLab. But if you had something that could cool it, and you could have a negative response, the output could go negative, then at 1.27, I think that's where our stability limit is. And you can see it went from kind of a ramp to now it's going to go down with this exponential and then go to negative infinity. So if we had infinite cooling, I don't know how this would be possible below negative 273, but this is a simulation that shows the controller is going to be stable if we had unstable if we had no output limits. Okay, below the negative 1.27. Alright, so you could go in and implement this if you'd like, but I think it's just sufficient with the simulator. You see here we can predict how much oscillation there's going to be with these different values of the KC. Alright, let's go back and just summarize on this. What we've done is we've developed a second order model of our system, and then we did a number of analysis techniques to determine the stability limits. We estimated this from the data to get Kp, tau s, and zeta. And then we also used a Peony simulator to tell us what would be the expected response of the TCLab if I plugged in a certain Kc value. Alright, here's the Routh array. Again, we can calculate that our stability limit is going to be -1 over Kp. And then we use the root locus plot to confirm that, but also determine where oscillation is going to start.